Okay, so Steve asked me to talk about protein aggregation. It's a very old subject in a way, because all of the work which has been done with proteins from the very earliest stages, obviously you're taking a body fluid, a molecule is stable because it's in that fluid, and you're isolating it. It has none of those. I mean, particularly in our blood, we have albumin as their body, 40 gram per litre, 40 to 50 gram per litre. And albumin, again, a lot of people making a protein, they actually stabilize it, they put it into a solution of albumin. So molecules are not all bumping into one another or whatever, and they've got clouds of other molecules around them and so forth. So it's been right there at the beginning, the theory of proteins and protein structure. Because if it aggregates, that means actually it has denatured, treated it badly, all sorts of things. We're much more sophisticated now, I think, in understanding those things, but still it is a sort of a foundation. I've already mentioned the fact that in that context is that any biological therapeutic is also similarly has been, even if we produce CHO cells or whatever it is, but what you're giving the patient, something which is ultimately purified. Although, again, as a therapeutic, you have to establish a shelf life for it. So every biologic therapeutic has a shelf life. So after 18 months, or whatever the innovator company put on, 18 months or 2 years, you can't use it. Why can't you use it? Why is there a shelf life? It's because it's changed. It's been changed. It means that it's been denatured in some way. And usually you find you've got aggregates. You have all these different, continuously more refined techniques for not only detecting aggregates, but working out, determining the size of the aggregates. And the size of the aggregates, as I'll illustrate, this all comes back from very early days in immunology. In fact, when I first went into the med school, I did chemistry first, BSc and PhD, then moved into the med school. And when I used to be teaching students, again, about immunogenicity, it fell to my lot. And the thought at that time was any small molecule, it's not immunogenic, and you start to put a size on it. And I reckon that at that time I was thinking anything about 10,000 molecular weight was likely to be. And if it's a naturally occurring molecule, of course, we know more now. We know about the innate immune system. So if you're looking at a bacterial polysaccharide or protein or viral protein or something, it's like the innate immune system can recognize it. There's receptors on macrophages and so forth. They ingest it and they process it, and they are antigen-presenting cells. So there it goes. There's no differences for that. Penicillin can be, people can be allergic to penicillin. Very early on in penicillin, there were a lot of people that were allergic. And then that was found, the particular penicillin they were using then had a disulfide bridge in it, and it was unstable, it was opening up. And then it was binding to albumin, and albumins were acting as a carrier. And now it was being presented on a high molecular weight molecule. With the antibody therapeutics or the biologics, we know when you're producing them that you can get aggregates forming in it. So, it rings warning bells right away. So we do all sorts of things to try and overcome that. And what I'm going to say to you, though, is, so we know that's the case. Okay, I'll add something else that I said before about the game multiple myeloma, in which we have antibodies from humans, human monoclonal antibodies, but we don't know what the antigen is. So we were studying that when I first came into the field, and we had a protocol that we used to use then. We would actually heat aggregate them purposely. We couldn't make immune complexes because we didn't have an antigen. So we made something as similar as we could. And we discovered Fc receptors and complement activation with those heat-aggregated molecules. So they were mimics for antibody-antigen complexes. So I'm linking up now the fact of chance aggregation of molecules, which maybe for a lot of proteins is good. We get no aggregates there and give it to the patient, no problem. But for antibodies, it's rather different, because you've now you're aggregating, you might make an immune complex. But for the last 20 years or so, this area of physical biochemistry basically has focused on aggregates as being the cause of immunogenicity of antibody therapeutics. So I wanted to look into that and might be heretical to suggest that immune complexes, in fact, should be considered alongside them. I gave a talk in San Diego a few weeks ago. Well, they couldn't get at me because I did it from my office and did it on the web. But, I floated it there. Nobody shared it. Okay. So looking at it through, then there's the isotypes. You now know, obviously, that the different isotypes are likely. We have to treat them, each of them separately, and also the specificity of complexes, mechanisms of action, heterogeneity, immunogenicity, tolerance. Okay. So make an obvious, or maybe it's not obvious. If you look across the surface of a protein, now you know. A protein folds, so the hydrophobic residues are orientated in towards the center. Hydrophobic residues interacting with each other gives the core strength and profile of that. And positive, negative charges are exposed on the surface. Now that's okay, say that, but it isn't 100%. You have some hydrophobic patches may be partly exposed on the surface, and you have some ionic positive, negative charge groups that actually might be quite buried. And we can actually, from X-ray crystallography, so go all around over the surface of the molecule. Usually you do it by, theoretically anyway, rolling a water molecule across the surface, right? Because proteins have water hydration. And so what's the accessibility and so forth of those? So this is that's running over the surface of an IgG molecule. The red are the hydrophobic patches and the blue hydrophilic patches. So you see there are and in fact, we see like with the Fc receptors and other things, the protein-protein interactions for physiological mechanisms is often hydrophobic interactions. So having some hydrophobic patches on the surface is actually essential to some biologic profiles. So here from Chris Roberts is a nice illustration here of remember again any molecule is mobile, right? It is breathing, as I say. Again, I quote another Nobel laureate to you, Max Perutz. I'm sure you've heard of him? Eh?
Because we had a lecture about it.
You did? Oh, okay. Well, he's the hemoglobin, metaglobin man. Right? And I remember, I dug it up recently, actually, an article in Scientific American in the early days of that. It was the hemoglobin, methemoglobin. And if we look at the binding site for the oxygen, there's a tyrosine residue there. Huh? You saw this as well. And it's in a certain orientation. And it can move into another orientation. And I reckon if that mobility was not, if it was permanent in that orientation, you get one oxygen atom binding every 10 to the 7 years or something. Absolutely depends upon that flip. I don't need to tell you what it's. Okay, so there is this natural movement of the molecule. If you haven't got the right pH, or you haven't got the right other things around it, then it can open up and expose more hydrophobic area, and another molecule has done the same. You've got the two hydrophobic areas coming together, and as the whole thing can then grow up, and you can get increasing sizes of these. Again, there's the size of the complex that is being formed. Importantly, again, depending on the conditions you use, it may be reversible. So you may be able to put it under a condition, you can do some physical chemical measurement, you know that it's partly unfolded, but if you reverse the conditions, it'll go back again. More extreme conditions, you may open it up and now it cannot no longer reform. This is denaturation, this is all these sort of things. It may come also, chemical modifications. So again, we've got these charge groups on the surface of the molecule. Asparagine, glutamine are susceptible to denaturation. That gives you then aspartic acid, glutamic acid. You change the charge on the surface. So all of this changes the character of the molecule significantly. If you want other examples of closer to home denaturation, I had a Christmas present a few years ago of making cheese, and just take that nice milk, and all you do is add some citric acid to it, and there it goes. It's just pH. You can go about. So it's very easy and dramatic. Well, okay, if you fry an egg. So there's been a lot. You see, the FDA and the EMA focused in on this, as has particularly. So if you know some of this stuff, John Carpenter, do you know that name? Okay. John Carpenter, yeah. And, I've been to his. He has every 2 years or so. He has these conferences on protein. I've been there to those meetings. This is Amy Rosenberg, who is a very high official of the FDA and has pronounced on these issues over the years. And so here's other ones here, and there's Chris Roberts ones here. And been a great deal of emphasis on this particle size question, particularly because you didn't know how to size them. You don't know how much would be there, and they get filtered through the 0.2 micro filter, I think it is. But there are these small aggregates that will still come through that. So, again, aggregation is equated with immunogenicity. If it's immunogenic, then it's the most likely cause is that it's there. Again, the definition, self-associated protein species. You can read that for yourself, and you have it in front of you anyway. There are lots of the slides that put in, so you have the information you have. We don't need to dwell on it as we go through. So it was rather, in a way, based on some of these studies, which I remember from way back, well before all this, which is viral proteins. Right? You know, the viral coat protein, which is very symmetrical, geometric, and so forth. And it's made up of a protein, which actually then normally forms a polymer, and then those polymers aggregate together, and here's the capsid, the final capsid. And the study, as you see here, was of looking at the immunogenicity of these monomers, the polymers, and the capsid, and the full capsid. And you see what the result there in these studies is the polymer itself was small and was not immunogenic. As soon as you start to aggregate it and so forth. So that's the practical as well basis for the question. Of course, we knew long before that also with larger particles that the macrophage will engulf them, take them in as even, do you know the name George Bernard Shaw? Poet and playwright. And in one of his plays, he talks about the macrophage, because Mechnikov was who defined the macrophage back in 18-something. So it's been around a while. And this was sort of summarized again from the FDA here, with the important part of protein aggregate studies evaluating the biological activity of aggregates, because they can differ quite dramatically because of the sites in the body that they can reach, amongst other things. Differences in monomeric aggregated protein profoundly influence the potency, and we see that with some of the biologics. You can exploit it again. Sometimes you can get, by aggregating it, you can cross-link more receptors on the surface and get a higher thing. So it's something you can use to enlarge it sometimes. But at this time, anyway, there isn't now either. There's no consensus on the maximum allowable limit for protein-based pharmaceuticals as aggregates. Okay, I'll come back to that statement later in having discussed immune complexes. So here we are, some immunogenicity of pharmaceuticals. And we talked obviously earlier about the generation of the first fully human antibody. Nirvana. We've succeeded. It's Humira. The incidence of 5% was in a study of the WHO, and in fact, when it was just Humira, the immunogenicity was about 12%. But you can reduce it by giving a mild immunosuppressant, in this case methotrexate. And if you do early rheumatoid arthritis, often the first line of treatment is methotrexate, a mild immunosuppressant. And some patients early on, get them very early on, and they will benefit from that. So it's an autoimmune response. It's an autoimmune disease. So then it went from 12% down to that. The 89% is huge, obviously. Explanation for that, not sure yet. I've just been recently, I'm in touch with the world expert on the polymorphisms in immunoglobulins. Do you know the name? No. Marie-Paul Lefranc. And we were looking at it together and see that in fact that Humira antibody is using a heavy chain V gene that is absent in a proportion of the human population. So whatever else is happening, there you see that as well. In fact, also if you take Rituxan or Herceptin, it is one heavy chain allotype only. And yet you're using it across an outbred human population. So there are immunological barriers there all the time, not just the physical form of the molecule. So that's that. Remicade, here you see some differences because depending on the disease. Here, Remicade, put that in here, 23, 27 for the biosimilar, that first one that is there, but that's good enough. Campath-1H, I'll come back to that one, that's very high. Originated, that was a rat monoclonal antibody that was humanized. And here too, quite interested here, Interferon Beta, produced in here CHO cells. It is normally a glycoprotein, and so it's glycosylated here. In producing E. coli, it's not glycosylated. And it's less stable, and also it's less stable. But it's approved. It's still there. It can still be. So some of the other parameters, again, influencing antibody interactions and the same formation of immune complexes. There's the patient population, the polymorphisms, obviously is HLA, with autoimmune responses, IG, FC receptors, a whole gamut of things. You all know you're unique, just by looking at yourself. But deeper underneath there is also all those unique things that are unique to you. So you're not going to respond to the same drug in the same way as anybody near you. Immune status, immunosuppressive medication, again like methotrexate, the dose, the frequency in the route of administration, whether it's given intravenously or given subcutaneously, makes differences for all of these figures that are coming through. Re-exposure to the immunogenic, sensitizing, tolerating, and of course, actually, again, talking about stability of the molecule, is the formulation. You produce it, you purify it, and you put it into a vial. And erythropoietin, there was a decade or so of benefit of that. And then in Europe, there was suddenly a group of people who got pure erythroplasia. They're producing antibodies to the erythropoietin. And in fact, at that time, comparing with the United States, the change had been made. So they'd gone from albumin to try and stabilize it to using a polysteric acid, I think, which was being quite widely used. But they also saw the cap was somewhat different. In the United States, they had a polymer coating it, so you didn't make direct contact with the rubber. And in Europe, it was done away with that. And the glass, because glass is actually a charged surface. And that can do little clusters of aggregates, and then you can get it spread throughout the whole thing. So there's a whole group of people who then had poor erythroplasia and had to be maintained on frequent transfusions. And talking about the molecules in that way is just this section, just over here. Again, application route, patient features, what is the disease, comorbidities, etc. Dose, concomitant medications, and we still put in still a question mark for so many other things. Right? So, plenty of work for you to do in the future. Mitigated isotypes. Again, just go back and said that. I've said that now. These can be separate lectures at different times, so there's a bit of some repetition in the subclasses again. Okay, right. Oop. So this actually again partly a summary. The first thing is the uniqueness of the antigen binding site, which the structure on the antigen which the antibody binds to is referred to as the epitope. Familiar? And the antibody, the actual binding site of the antibody is referred to as the paratope. So we've got paratope, epitope recognition. From work that was done much earlier, in fact, like with the myeloma proteins, we put these myeloma proteins into rabbits, usually make a rabbit antiserum, and you could always, no two were the same. Now, here, we're talking about allotypic determinants. So you have the isotypes, below that you have a differentiation into allotypes, and underneath that was idiotypes. Idio meaning more or less unique, as in an idiot. It's the village idiot, someone, a unique personality and character and so forth. So the idiotype, and lots and lots of work is done there. So, and so the antibodies, the therapeutic antibodies are generally anti-idiotypic antibodies. So it's terminology which is used. And again, outbred human population will not have seen an IgG molecule of that unique structure. Again, in the FC, we have the polymorphisms, and these allotypes, polymorphic forms, were actually first discovered, human ones, were discovered with human serum. This is multiparous women who can, after third and fourth pregnancies, sometimes produce antibodies against the paternal allotype. And also be multiply transfused individuals. There is no control is not made for allotype in terms of do so. And again, from time to time, you get that. So they were discovered with human serum. So they can be immunogenic in humans. And we do not match the patient to the allotypic form. And again, to show even further here, rheumatoid factors, as they're called, which is the autoantibody, which is, you see in patients with rheumatoid arthritis, is directed against the patient's own FC. So again, that's a whole decades and more saying there must be a change in the structure of the patient's own IgG to make it foreign to its recognized method. And we see, of course, in many autoimmune diseases, you have antibodies directed against self. It should be self, non-self discrimination, which is the key requirement for them. And as I have indicated before, depending upon whether it's a monoclonal antibody, depending upon the cell line that you've used to produce it, so there may be differences in the glycosylation, and adding these sugars, which are there's antibody, forming antigen-antibody complexes. Done. Good, nice lab experiment of many years ago, getting rabbit antiserum, etc., against anti-albumin, human albumin, or something, and you just titrate them, and you can go through titration here. Where you've got a lot of antibody, you add a little bit of antigen, and you get some complexes formed, and you can carry right on into antibody excess, and so clearly. In antibody excess, you'll have some antibody molecules. Now, there's not enough antigen to do it. And any complexes you get are going to be small complexes. And similarly at this end as well. And if you do that titration, you then find there is a point in the middle where you get maximum complex formation and you get precipitation. And that was, again, many decades of techniques that were given, Octoloni analysis and so forth. So we are making aggregates. We're making immune complexes which are aggregates of the FC. So what we're looking for in an immune complex is, in fact, for the FC things to be clustered so they can cross-link multiple receptors on the surface of the cell. If you just engage one receptor, it doesn't activate the cell. All of them, they come back and cluster on the membrane and it goes. So that's why how they function in vivo, forming immune complexes. And this shows here now, so go away from that now and look at, we've got an antibody therapeutic, and we're trying to get the right data to go to the regulatory authorities and see the developability of it. What can we do with it without it aggregating, precipitating, doing all things we don't want to do? So we have to analyze it for that place. And so what we use is accelerated storage, or accelerated things, changing the pH, taking it up to 40 degrees. We can't, we're hoping for 2 years, but it'll be very slow progress if we kept on for 2 years all the thing. So we're trying to do this accelerated degradation to try and put a shelf life on it. We've got to be able to do that. So here's a study in which is the native was nice, clean on size exclusion chromatography, and then it was pH stressed over a period of time, and now you see that it's forming aggregates. This is the size, obviously, and different families of aggregates. If we go on, it'll gradually go more to the left. Mass spectrometry was then, years ago we didn't have that, now we do, and you can characterize the aggregates much more precisely with mass spectrometry. Other parameters that influence the architecture. I'm talking now about the architecture. Not just have we got them of a certain size, but actually are they in strings, are they just in spheres, or what is the actual architecture and the display? And don't forget also when we're talking about then forming immune complexes, because your IgG is divalent and so it can cross-link, with that hinge region, that's why it's needed, so the FC can be available, accessible to the FC. If you chop out the hinge, then you won't get the same activation. So there's the isotype of the antibody, the valency, again because of its IgA, and it can be 4, IgA dimer. IgM, how many for IgM?
10.
Always? Do you want to qualify that?
And when it's in a pentamer form, it's 10.
In a pentamer form, it's 10. We've got five IgMs, but actually, functionally, usually it isn't. It's only 5. IgM does not have a hinge, and usually, and when you any size of antigen, when it binds to one paratope, it sterically occludes the other. Small molecule, small hapten, or something or other, 10. So, the avidity, or avidity, is there a distinction between affinity and avidity? No? Affinity is something which, if we talk about and people use the term wrongly, talk about the affinity, high affinity antibody and so forth, and you can't measure the affinity of a divalent antibody. It has to be one valent species to interacting. So you can talk about the affinity of an FAB fragment, but when you have two binding sites, because if you're looking in the mass here, so you're looking at one FAB, it binds to the antigen, right? So affinity. Now, well, maybe both of them, but now it's a reversible reaction. So this one disengages, but it's being held in the proximity of the antigen by this one. So it's more likely actually to come back and bind again. So that's affinity. Avidity, rather. Avidity. So the more binding sites in IgM, high avidity. Low affinity, high avidity. 5. At least 5. The epitope specificity, epitope density on the antigen. Again, if we're looking at CD20, like in leukemias and so forth, we're talking something about 100,000 molecules on the surface. Different cell types, be different, anything from possibly as low as 1,000 and up to over 100,000. So that makes a difference as to how you can occupy the site. Lipoform profile, of course, effector ligands engaged. So quite easy, nice study that one can do is again in rheumatoid arthritis, ulcerative colitis and so forth, where it is the therapeutics are anti-TNF, TNF alpha. And we have 3 whole antibodies that are approved. Chimeric, adalimumab, Humira, which is the human phage display library, and golimumab, which is from a transgenic mouse. Here, etanercept, Embra, and what they did here, because of this question about here, that you could get some of the biologic activities activated, went a nice way around that, and also about forming complement. There is the TNF receptor. There's 2 TNF receptors. So if we, okay, just a transmembrane protein, so we just make the ectodomain, it will bind to the TNF. And put it onto the FC here, so we've got the long half-life. So that's a fusion protein. And then here, the other one, the certolizumab, which is the FAB, an FAB fragment, anti-TNF, with the polyethylene glycol tail on it. So we look at those. So here is infliximab. What we're doing again here now is titrating the antigen with the antibody and look at the immune complexes that are being formed. A different antigen-antibody ratio. So keep the antibody constant and putting in different amounts. Here's the ratio of antibody to antigen going through here, and very clearly you get all of this interesting, if you like, profile, whole heterogeneous profile of aggregates form. Only seen like this because TNF automatically, naturally forms a trimer. So you've got at least 3 epitopes there. If you just take the single molecule, it would only be 1, so you wouldn't get this behavior. But it does. It's a trimer. It's a nice study by the group in South Korea. They had actually produced an anti-TNF antibody of their own, different epitope, same titration of epitope, and you see a very, very different and distinct profile of complexes that are formed. So again, we could expect them to elicit different responses. And here's etanercept. And that is just giving this one restricted time. Etanercept is the least immunogenic of these therapeutics, in fact. I showed these data to this meeting in California, San Diego, and immediately got a Japanese gentleman who came through to me with a paper, and he's repeated rather this work with now a bit more sophisticated analysis, and sees exactly the same here, that etanercept can only form this AB1 AG1 immune complex. This is his work, in fact. It was published in 2017. So I updated the study. So adalimumab, you appreciate that, and you go through that later. I don't need to take you through it, I think. Just as sort of personal note, okay, we did quite a lot of that. I did some work with a chap from Denmark who had actually done a computer profile of possible immune complexes being formed many long time ago. Doing ultracentrifugation, Steve Harding would be pleased about that. Anyway, but from that, we have produced lots of antibodies. Most antibodies against human IgG, and we defined ones for specific with the subclasses and all sorts of things. And suddenly, the work we did with Jens Steensgaard, we were actually looking to see precipitating immune complexes reform. I went over there to do some studies, and the centrifuge was down, so we couldn't do it. So he had some light scattering equipment there, so he said, well, let's look there. So I thought we'd have to add lots and lots of different antibodies there. In fact, we added one antibody, then we added in the second one, and it just went. So we patented it, and we've actually developed, since we formed a company later on, and here we've got an antibody to human light chain, constant region, and here to the far end of the molecule in the FC. So we know that they can both bind, and in fact they do so, and they form complexes and so forth. And then coming decades later, we actually formed another company, and have put this into modern technology for actually, in particularly multiple myeloma, a number of leukemias, the ratio of IgG molecules that have kappa chains or lambda chains is different. We know that it's usually 2 to 1. And you can do that, and if it's moved one way or the other, you know that you've got a clone of cells there overproducing free light chain. Free light chain. So it's difficult to get the specificities. And the company has been taken over now by a company, Abingdon Health, still with us in the university, and it was used recently here by NASA to follow astronauts well before they departed, whilst they were in space, and when they came back with a control group and so forth. So we're pleased about that. Mechanism of action, you see that. Again, so anticipating that depending upon the kind of immune complexes that are being formed, so we'll get a different outline. Where else can we take it to exemplify things? Here's in leukemia, the CD20 molecule on the cell on the surface of B cells, and here's the first one that was approved, rituximab. Here, this is X-ray crystallography superimposed here of here's the CD20 peptide. It's just a small bit of the ectodomain outside, external domain that the antibody binds to. But there's another antibody here, obinutuzumab, which also binds. So it's a very small peptide sequence, but they both bind, but in different ways. But they activate different mechanisms of action. So the rituximab is complement activating, whereas obinutuzumab is direct cell killing. That is apoptosis. Some antibodies, they could go over, they bind onto molecules on the cell and drive it into apoptosis. So radically different. mechanisms. This is a third antibody, the CH7, which has different orientation again. Even though, here's the epitope, so the epitope specificity, this is just this small peptide, which is that external domain, which is the target for those antibodies. And if we take, where is it? This protein residue here, protein 170, if you exchange that for, let's say alanine, which is usually we do, you lose the binding of all those antibodies. So it's conformational. They're overlapping, non-identical epitopes, but the architecture of the immune complex that's formed is different, and it moves the mechanism, impacts the mechanism of action. Just another illustration looking at this helix upright and so forth.
I've got a question, Hans.
Yep.
So would you say both of the mechanism of action are activated at the same time, or like if one gets activated, the other is
No, they will block one another. You can't use them both in this case. We'll have another case in a moment where I think I've got it there, which partly answer that. So they have different actions. So what is actually happening here? So what we see is that CD20 is expressed on the surface of the B cell as a tetramer. And the rituximab cross-links those tetramers. And in fact brings them all together on the surface of the cell. And then they're endocytosed and so forth. Now, obinutuzumab is different. It cannot span those tetramers. So it's not opening out in the same way. It is actually satisfied. It cross-links across the tetramers, and so all the molecules are not brought into a patch in the centre of the cell, and therefore activate complement, because rituximab. Remember I showed before about the galactose and so forth activating complement. So rituximab can activate complement. You see the ADCC, CDC, apoptosis poor. Here, ADCC good, CDC now weak, and apoptosis. So HER2, breast cancer. Trastuzumab, Herceptin, is the first one. So here's the HER2 molecule in the background here, and trastuzumab has, of course, been very effective. It was the first one. Again, good, so everybody else wants to try and get in on the map. And pertuzumab was generated, and it also is effective in breast cancer, and you see attaches to a different part of the molecule, so they can't do that. It needs a high concentration of the HER2 protein on the surface. It's only about 1/3 of breast cancer patients who actually go forward for this, because they don't have a high enough HER2 expression on them to be successful. Of course, it's hugely expensive. So again, you're always trying to increase it. And here, you can actually use them together. They can be accommodated on them, and use the two together in combination, and you have a more effective therapeutic. Again, architecture of the, how do you get it? What does it happen? What does it do? This illustrates another point, because when you're doing these studies, you generate an antibody and you're looking to look at the mechanisms of action, and we use cell lines, human cell lines, of breast cancer, leukemias, or whatever. But each one of those is unique. So, of course, so you're using it here, ofatumumab, and here are 3 different cell lines. Well, look at rituximab. Cell line, see, nice, and ofatumumab is similarly. Dowdy cell line, Raji cell line, which is widely used, nothing with rituximab. but it is of a tumour. Another way, so again, the care that you have to take in trying to assess when you're doing research and probing molecules for their biologic activity. So that was GSK and Genmab, which is a Dutch company. GSK is UK. Oh, I went the wrong way. Another illustration, if you will. This, okay, so what we've taken here is looking again at the epitope expression, epitope density. So we've got BSA, and we've put trinitrofenol group on it. It's been used a lot in many wide studies and sensitized in mice to so here we've got 4 TMP molecules on a BSA, and here we've got 26. And what we're looking at here is that's the control, and here the immune complexes that are being formed, and you can see along here, particularly here, how the epitope density, the epitope expression is impacting the Fc receptor binding, this Fc receptor binding. So basic immunology, B cells, T cells all start off in the bone marrow, mature in the B cells leave the bone marrow immature in the circulation when they're expressing IgM and IgM to begin with. When they express IgD, then they are mature, and we need T cell, B cell collaboration. And of course, during that process, it's supposed to have eliminated any self-reactive cells. I mean, we know again that's not 100% true, but it's the foundation on non-self discrimination. So if it's low, again here is where affinity is an absolute requirement. Whether a self-antibody binding to a self-cell, if it's a very low affinity, goes on and off all the time, it still has some ability, it binds, but it's not going to be active, it's not going to be effective. And as you may know about checkpoint antibodies, have you done checkpoint antibodies? So actually, we know that, again, that is under regulatory control, and you can bypass that and again, improve therapeutic antibody. Low affinity immune responses to counter antigens do not eliminate cancer cells, with high affinity interactions. The cell can result in autoimmunity. So always there's a payoff somehow here. It's a dynamic feature. Well, you're all dynamic, even if you sit still. Repeatedly, I think if I've got my things right, you're going to take a look here at CAMPATH1H, which you see is a highly immune. No, I'm going to go back a step. I've obviously spoken about the heterogeneity, which is inevitable in a protein, but also, because all protein in the body has a half-life. It's turning over all the time, and it undergoes degradation. It's a natural part. Deamidation is one of the first ones. Now, there are certain of the asparagine or glutamine residues that are exposed and get deamidated. If you put it under stress, you open the molecule, some other ones that are not normally deamidated become deamidated. Now it's a denatured protein. Well, with recombinant proteins, therefore, it's not going to produce a product which has got to have the same profile of heterogeneity as you have for the molecule in vivo. So you see it, deamidation here at pH 7.5 principally is asparagine 384, 389 in the FC region, which is most susceptible to deamidation. At pH 5.3 is an asparagine 325 in the FC part of the region. Now, what is the consequence of that? Well, again, then you have to analyse the best IgG that you can get hold of, which would be normal serum IgG, and you see, actually then you see 23% asparagine residues at 384 are in fact deamidated from serum IgG. So we don't think that's a problem. Up to 23% of that, your normal serum IgG has got that amount of deamidation on. But when you're getting 389, 325, which is not, then it becomes a problem. It's getting tired. You're not, are you? Deamidation again here. Then we know that the FAB succinimide formation at asparagine 55. I left out what the antibody is. I think it's just an example of an antibody where asparagine is in the binding site, in the complementarity determining region 2. So what we learn from this, from deamidation, is we don't want, when we're producing a monoclonal antibody, we sequence it, we do the structure on it, we don't want to choose one which has got an asparagine in the paratope, in the binding site. We don't want a methionine, because you see, they can be oxidized. So you're going to select on it. This is what they call the developability of the molecule now. How stable is it likely to be? We want to avoid, so that's what we learn from these studies. And again, with Herceptin, asparagine 30 and CDR1, gives some loss of potency. In the heavy chain, 55 in CDR2, and asparagine 102, which converts to isoaspartic acid, so it leads to loss of potency. My very good friend Reed Harris at Genentech, very, very nice data. Okay, I'll go back. Methionine oxidation, see here, again, so 2 to 5% of methionine 252 is seen to be oxidized, and IgG isolated from serum. 80% oxidation reduces serum half-life. Well, we're not likely to get that on storage or so forth. So these are the kind of things that you're doing to try and see how you protect your molecule, put it under stress over a period of time, choose the right conditions of formulation, everything there, before you go to the regulatory authorities. Not before necessarily, because you can go to the regulatory authorities. People used to think they've got to get everything, dot the I's, cross the T's before they go there. Now regulatory authorities say, come to us and discuss your work once you're getting on. Because there's been a lot of work in the emphasis in the USA to get more. Europe has been far ahead of the United States in approving biologics. Deamidation of arginine, that happens, and we see it in autoimmune diseases, and it gets deamidated to citrulline. Now, in rheumatoid arthritis, they have antibody, anti-citrulline antibody. It is now the most definitive diagnostic feature. So diagnostic is that they make a small synthetic peptide with citrulline in it, and that's the diagnostic assay, not using the whole molecule at all. So, not only are these changes likely to lead to having an immunogenicity and a mental response, but you see they're also linked up with autoimmunity. They're the same things that happen that we see in autoimmunity. As is shown here, in fact, rheumatoid arthritis or filaggrin is one of those deamination, the arginine. Celiac disease, alpha-gliadin, but it's not the natural form, it's deamidated. Systemic lupus erythematosus, phosphorylation, autoimmune encephalomyelitis as an experimental one, but deamination and so forth. And it's an aberration in these modifications that's important, because the deamination here is that we have an enzyme that causes that deamination. Here it is, PAD4, and we all have that, and we all need that. But it's got to be modulated, it's got to be controlled and modulated. Get it out of control and modulation. And so you think the immune system, it's got to be on a knife edge. It mustn't have all these severe inflammatory cascades. On the other hand, as soon as it has an insult, it's got to come in immediately. So it is absolutely on the knife edge. Yes, so this is a candidate biosimilar molecule here, a paper that's published a long time ago, as you see now, and just underlines the point to say is that they came through with a rapid way of analysing an antibody and to sequence it. And they came through and they gave these values for deamidation and methionine oxidation and so forth. It was a Genentech antibody, and again my friend Reed Harris saw that, and he knew that that was not the right figures for Genentech's rituxan. He had his own data, and so he got in touch with the editors of it, and so this note was added in proof of the paper, which is that therefore that they had obtained it from a pharmacy, the rituxan, which is what you have to do to make it, and they had not treated it kindly when they took it into solution and did the analysis on it, and they had got more deamidation, more methionine oxidation than the approved product. So it's easy to do. And that comes in very much now, of course, okay, where you call it, the antibody comes into the pharmacy, who now makes it available, ready to put into the patient. Is it done in the pharmacy? Is it something which is done at the bedside? Or some things like that also, which actually I've got some, reminds me I've got some other papers here. Come on. FDA, again, because of all these different things, and because it's a large molecule with something usually about 100 of each of the amino acids there, in different arrays, then the FDA said, well, you know, if we take each one of those in turn and do it, there could be 10 to the 8 different molecular forms of a molecule the size of IgG. We hope that doesn't happen, but again, and again, don't forget, you know, again, all the differences that will be there because of the way of doing it. So how do we get out of that? I think maybe we need to actually look at going more at the immune system. So I've said about immunosuppression. So methotrexate, reducing here. Of course, the immune system is self-recognition, non-self-recognition. And it's, again, a dynamic process. If we understand it, we can maybe, again, use it to advantage. And it is being used to advantage. We look at tolerance. We can induce tolerance. Two methods, giving very, very repeated small doses of aggregate-free antigen. And it's being used in desensitizing people with allergies. Now, it was done years and years ago, but it was an extract from pollen, and it was not clean enough, and I had some deaths. Now it's a recombinant allergen. It's clean. We can do it. And we can give aggregate-free protein and build up tolerance. And this young lad here is enjoying some peanuts. And one of our daughters, one of her classmates, went to a party and died from cake that had some peanut in it. So dramatic. Take another one, this Campath-1H, alemtuzumab. In fact, it's proved for a number of conditions, 74% of patients develop an anti-drug antibody. It's widely expressed. CD52 is widely expressed on lots of cells, so it's been used in a lot of different clinical conditions. Been around for a very long time, again, Cambridge group, and then you move to Oxford, and they've done an X-ray crystallography, and see, looking at the antigen binding site, to see that actually there is a lysine residue here, 53, and it's obviously crucial to binding. So they thought, well, to prove that, I mean, we'll change it from a lysine, which is negatively charged, positively charged, to aspartic acid, which is negatively charged. They do that, and they produce a new molecule. It's exactly the same as everywhere else, SM3, but they've gone from lysine to aspartic acid, and it now doesn't bind the CD52. Then they took a leap into the dark, not into the dark, a very courageously, I would say. They said, okay, we know this is very immunogenic. If we give this a group of patients this SM3, which is only different by one amino acid, but doesn't bind the antigen, maybe we can induce high dose tolerance in the individual and follow it up. And here's the result. 212 patients, they did not have SM3. 1 month post exposure, 30%. Here, 20 patients who had the SM3, nothing, and they carried through to 13 months, by we're now up to 80% here and 21% here. Could we improve on it? But again, it's a possible way forward. Okay. Work on this, and this might be the way, a better way, in many cases. Okay, say in cancer, it may not be so important. Patients are always going to have chemotherapy, and that's going to suppress the immune system. It is chronic diseases where you're treated continuously or you have episodically. And we certainly again know that if you have a course of treatment and you get a good response, so you don't expensive stuff. You don't carry on treating them, and then you get a relapse, and then you find the immunogenicity is higher when they're exposed again. So there it is. So what's the difference? We're using the SM3 and the antibody. It doesn't make immune complexes. We're not getting aggregations. We're not making immune complexes. So. And of course, again, it's just the same as using aggregated material. You've got the same outcome. Herceptin, again, paper 2013, somebody noted that the instructions for preparing the Herceptin for infusion were so very, very precise that many people stabilize it with sugar, dextrose, that you must not use it. So somebody said, why is that? And so they took it and they put some dextrose in, precipitated, straight out. So you must not, and the same is for Avastin, both from Genentech. Absolutely precise. But also, but most of the other antibodies they'll be stabilized with sorbate or dextrose or other things. So it went one further, the FDA went one further in fact with this and said, well, okay, but when you infuse Herceptin, it's going to come into contact with sugars then in the serum. So they then, instead of looking at that, they then did it by mixing with serum. And as you see here, you get this isoelectric precipitation of plasma proteins, which the C3, C4, factor H, and so forth here. And so the Herceptin becomes co-precipitator out of the complement proteins. So. I came across this a couple of weeks ago. Here, maybe the panacea. So somebody here has just made a library of peptides and has screened them, just random and screened them for interactions with molecules in IgG. And they've got this molecule, it's not based on anything other than screening tens of thousands or millions of small peptides. One here that actually binds to IgG in an aggregating prone position and seems to block it. Now, that was 2018, it's only just in December 2018, so we've got a long way to go before we believe it, or accept it, or develop it, or whatever it may be. And there we go. So, that statement from the FDA about protein aggregation studies evaluating molecular activity, differences, etc., I modify that and say an important part of immune complex studies, evaluating the biology of the complexes, differences between monomeric and immune complexes, they influence the potency of an antibody, and there's been too little study of immune complexes. I rest my case. Anything? Stunned? Let my people go. Okay, well, I hope you're enjoying your Nottingham experience. I think it's not nice, is it? I've been here quite a few times, and I like the centre, the way they develop the centre of the campus there very nicely. Birmingham is following suit now. Just going to open our Green Heart centre. Similar sort of concept, a big place where you can aggregate. Oh. Okay, please, thank you. There's no questions. And,